little whippersnappers. Here's your 8.1 overview, looking like at the last piece of material for the entire semester. All right, so looking at number one, all of these are taking a deep dive into Pythagorean theorem, the most elegant of all theorems. So we have our a squared plus b squared equals c squared. I put these legs in red so that we could see where these things are, and the hypotenuse c, I put that in a very nice blue so we can see here. And that's pretty much it. So we're given our two legs here. We square each of those. We get those values, and we add them together, and then we take the square root of that to get 97. So that's about all we have to do for that one. And the only other real option that we have for this, so number one is an example where we have two legs looking for the hypotenuse, and two, and I think the rest of these are examples of looking at where we have a missing leg and are given the hypotenuse. So it is an imperative that we put the legs, or the ones in red, on the left-hand side or right-hand side, depending on which way you solve it. And the hypotenuse will always be by itself. So we have 5 squared plus b squared is equal to 13 squared. We solve, and here we are with b equaling 12 for number 2. So that's what's happening with that one. In number 3, we are simply seeing if this is a Pythagorean triple, which just simply means it satisfies the Pythagorean theorem. So we do this. I square my 3 and my 5. I end up with 34. I square my hypotenuse of 6. I get 36. That does not equal each other. So no, this is not a Pythagorean triple. Number 4 is very similar to number 2. Except this time we're not going to get a perfect square. So that's only the difference. Setup is the same. So our red legs are here. Our hypotenuse is by itself. We set it up. I get the square root of 65. I am done. So it's not asking us to round this. It wants exact answer. Therefore, we leave it as the square root of 65. Looking at number 5, exactly the same as 4. Setting up our legs, 14 squared plus x squared equals 19 squared, our hypotenuse. Math happens, and we end up with the square root of 165, and we are done. Looking at a similar little word problem. So in this one, the difficulty is setting it up. Typically, the ground is here, meeting with a building or wall, and then we take a ladder and place it from the ground to the wall. Here you can see our legs here are the ground, 16 feet, and the building wall, which we don't know is x, and we know that the ladder is 23 feet long. So we set this up just like all of the others, and we follow through. This one, it is asking us to round to the nearest hundredth, so the square root of 273 is about 6.52. In number 7, we get a first opportunity to look at special triangles, or we can just simply solve it the way we've been doing it. So solving it the way we've been doing it, since we know it's a square, we know that our legs, or the red ones, are equal. So they're both x. So we square those, we end up with 2x squared. Our hypotenuse, or the walkway of the diagonal, is 16. So we square that, we get 256. Divide by 2, take the square root of that, and we're done. Or we can realize, like, ooh, this is a special 45, 45, 90-degree triangle. And those triangles have fixed outcomes. So our sides are equal to each other, so that is x. And our hypotenuse will always be side length times the square root of 2. So if we use this format to solve this one, we know that x times root 2 is going to be equal to the given diagonal, or hypotenuse. We divide that by the square root of 2, and we get the same answer. So you have two different ways to solve this problem. The choice is yours. Moving on to number 8 and number 9, we're being asked if these triangles are acute, obtuse, or right. And in knowing that, we have to look at this format. So if our legs, after we square them and add them, is greater than the hypotenuse squared, it is an acute triangle. If those legs, after being squared and added, is less than the square of the hypotenuse, it is obtuse. And if it equals, then it must be a right triangle. So number 8, I follow through and I find out that my legs squared are 52 is greater than 49, so this must be an acute triangle. In number 9, we're following the same format here, And when I square my legs and add, I've realized that they are equal to each other, and that must be a right triangle. Now coming in at number 10, we just have a large triangle that's comprised of two smaller right triangles. So since we don't have a right angle here, or we don't know that it's right angle, we just can't simply square this, and it equals 6 plus 24 squared. So we have to do it in two parts. So in first part, I take it and we look at this first smaller triangle where we have a leg of 6, and I've just simply called this dotted line, or this leg, y, and our hypotenuse is 3 root 5. So we follow through with the Pythagorean theorem. And just a side note here, when we're squaring something with a radical, each part of it is squared. So the 3 is squared, that gives me 9. Root 5 squared is 5, and when we multiply 9 times 5, we get 45. So that's where this comes from. And then we subtract our 36, we end up with 9. So we know that this part is 3. So if we look here at this triangle, now we can solve for x. And in doing so, I use what I just found is 3. That is one of my legs. One of the other legs, 24, is given, and I'm looking for the hypotenuse, which is x. So I follow through with the Pythagorean theorem. I come with the square root of 585. Since it wants an exact answer, we need to reduce this, and I'm looking for the largest perfect square as one of the factors. The largest perfect square that goes into 585 is 9. It goes into it 65 times. 9, the square root of that reduces to 3, and I cannot reduce the square root of 65, so we have found our final solution.